to what you saw in Revit. um, so do you guys recall the patterning exercise we did where we created a grid with rectangles and we had a magnet or an attractor point? Those two terms are somewhat interchangeable. So what we're going to do here is I'm basically going to show you that the same principle applies in 3 dimensions as it does in 2 dimensions, but it's slightly different, just a little bit different. So here's what we're going to do. Essentially, what we want to do is transform. So I want to go to transform and affine, and I'm going to grab scale, and I'm going to put it off to the right. So remember, I like to do this and put my goal off to the side a little bit and begin to work towards it so that I understand what information I currently have, what information I need, and that helps me figure out how to fill in the in-between. That's just a personal method of mine. So what I am going to do is scale a set of geometry. And I already know that that set of geometry is going to be either the surface box or the box volume. In this case, I think they're interchangeable. But the good thing about the box volume is that the twisted box list is a flattened list, and the box volume is an unflattened list. So it means it's set up in groups, right? N equals 1 means that it's in a group of 1. So that helps me organize the data in 2 separate ways. So while geometrically they're the same, they will read differently. So that's why that's kind of significant. I also need to specify a center of scaling, and then I need to tell it how much I want it to scale by. So the center of scaling for me is going to be the centroid of each and every one of these twisted boxes. The geometry will be the twisted boxes, and then the scale factor is going to be how far away each of those respective boxes are from my point, right, my attractor point. So that's how I begin to work backwards. So I'm going to begin with the geometry and the centroid first and try and figure out how that's actually going to connect. So when I go into surface analysis and grab area, let's take a look at what geometry we're getting. So can I grab a centroid off of surface box and get each and every individual centroid? No, I cannot. But I can, using boundary volume, get each and every individual centroid. So they read different, right? Because with twisted box being a solid, or what's the term for it? Oh, I forget. Anyway, so the solid format, right? So it's not a BREP, it's just a solid, actually has a centroid because it's reading each individual surface separately. It's not just a morphed original surface. Or something like that. So using those centroids, we are going to scale each and every one of these boundary volumes. So when I plug centroid in, well, yeah, I guess you wouldn't see anything yet because I don't have the geometry in there. So the geometry itself is the boundary volume. So I plug that in, and here you see that we have our twisted boxes are being scaled down by the factor of 0.5. If you hover over the F, it has a predefined scale factor, and it does that across the board. So that's looking pretty sweet, I think. But we want it to be more dynamic. I want to place a point in space, and I want to say that each of the surfaces that are closest to that point are either larger or smaller, depending on their distance. So for me, I'm actually just going to grab that point at the bottom, and I'll raise it up about halfway. If you hold Alt and use the gumball, it just makes a copy. So now that point is going to be my attractor, and it's going to scale each of these cells or forms based on how far away it is. So we already know that that point is going to have to be referenced in. So let's go ahead and do that now. So under params, we go to the point geometry input and set one point, and you can go ahead and select it like that. So I'll put it back here with the rest of my input values on the left. And here's the cool part. You recall the other day we did what's called closest point. Let me clean this up a little bit. It's getting a little wide here. We did what's called closest point. Well, closest point is applicable for three-dimensional geometry as well. So that essentially looks like this. So you go to vector, point, closest point, and take a look at the input values. So it needs a point to search from and a cloud of points to search. So the singular point to search from is that it's going to give us distances from the original point, right? Our output D is a measure of distance. It's a numerical magnitude. And then the points to search would be the centroid. All right. So then if you recall, when we were trying to set up the minimum and maximum values of our pattern, we used a remap. This is under vector point. We used what's called remap, and remap for us set up a domain that we used. Do you guys need a moment to get caught up? All right, I'll pause. So we've got our closest point measurement. If you hover over, well, you can't hover over distance because it's not a flattened list, but grab a param here, a panel under params input, and put D into it and just take a look at what it's reading. So it's actually measuring the distance from our attractor point to each and every one of our centroid locations. So for me, because I have a 1,000-foot tower, these ones fall somewhere toward the far end, right? And then it'll get a little bit lower. It should go down to about 100 or so, and then it should come back up. Okay, so that's what it's reading. And when we plug it into scale factor, right now it's essentially going to give you a really huge. Don't plug it into scale factor is what I'm saying, because scale factor is a multiplying. It's a multiplication function, so it'll scale each and every one of those things by 440 times its original size. So you don't want that.
That's a default scale, right?
Yeah. So what we need to do, like I said before, is remap that domain or those numbers to a smaller minimum and maximum range. And remap, you've seen this before, is under math, domain, remap numbers. Okay, and then what it's going to ask you for is the values, the original values that it's remapping. It'll ask you for a source domain, which essentially means what are the minimum and maximums of that list that you just fed me. And then it'll ask you for what domain you're remapping it to. So you can actually set up sliders for a domain, but because we're dealing with a minimum and maximum, relationship here, right? You don't want it to be any larger than its original box. 0 to 1, right? But also recall that if you do happen to have something that would be scaled exactly to 0, and if you're remapping, you will, you can't scale something to 0. You can't multiply it by 0. So to avoid errors, I always advise change your set domain to 0.01 or whatever other size you want it to be as at a minimum. You know, you might say, I don't want it to ever be less than 25% of its original size, and then you would do 0.25. But if you want, you know, as far as it can go, set it to 0.01. All right, so here's what we need to do. For the value to remap, that part's really simple. You just take the distances and you plug it in. For the source domain, right, it's asking you what the minimum, maximum of that list is. All you do is go into domain. You grab this node that's called bounds. Bounds will read a list of numbers, and it will give you the minimum and maximum. So also for this one in particular, because we're reading data that is broken out into individual groups, right? We did that on purpose so that we get them to communicate again when we're saying we want factor of item number 0 to go to factor of item number 1, so on and so forth. We need to flatten this list when it goes into the boundary. Otherwise, it's going to give you 112 different domains that are actually set to, for instance, if the first one is 440 away, it'll give you a minimum of 440 and a maximum of 440, and then it won't scale at all. So you flatten the n input, and then look at what your output is. It says one locally defined value of 127 to 511. So that's my closest and farthest.
When you're flattening it, is it dividing it by a certain amount?
No. Good question. So clarification on what flattening means. If I plug the distance numbers in, this is what you get, right? All of the values are set up in groups, right? And when we talk about data trees, that's essentially a branch, I think is what it's called. And so, what was I getting at? Oh yeah, so they're set up into each individual groups. So in this case, each group only has one item, which is under an index ID. It's like an ID number for each item of 0, right? But if we go back to, you know, the faces list, we've got 4, and see it's got a solid line, so that's coming out as a flattened list. Those read under index items of 0, 1, 2, and 3. So you can select those individually. But if I do a list item on this and I select 0, it'll still select all 112 separate groups because every single one of them has an ID number or an index of 0. Does that make sense? Mm-hmm. So when you have groups of information, you can get them to very easily communicate to one another, and that's how we did our space frame. When we did our space frame, we had groups of all of our centroids listed at index 0, and then we said, I want my centroid index 0 to connect to all of my quad leg points 0s, points 1s, points 2s, points 3s. Right? So when they're grouped like that, you can do multiple functions at once. Does that make sense? All right. So moving on from this, we've got our minimum maximum values, which then gets plugged into the source domain. And so what it's doing here is it's taking all of the numbers from the V input and it's saying, depending on how close it is to 127 or 511, I'm going to scale those down to a number that ranges from 0.01 to 1. You guys understand that conceptually? Let's see how it looks. So the output values here, we have the mapped numbers. And, well, don't worry about clip numbers, but yeah, don't worry about clip numbers. Oops. So plug in the remapped numbers into the scale factor, and now you'll see how it operates. So let me pull this aside here, and I'll spread it out again so you can see it, but I want you to first see the model itself. I'll turn the stairs, not the stairs, the slabs off, and now you can see what it's doing. The farthest point is the most full, and the closest point is the least full. And if I turn my box off, you'll see it even better. And my centroids. Got it? Yeah.
How do you turn out the slabs again?
For me, my slabs were up here. They were this extrude.
Oh, okay.
Remember that was from like early on last week on Thursday?
Yes.
Yeah, I was just thinking.
Alright, so we're going to play with this a little more, so I'm just going to pause the video right now and get you all up to that level before we go on.